Good morning, my students. It's about the time to start the class, okay?
Okay, Professor.
Well, let me finish my lecture today. I'm going to cover co-integration and do the example for co-integration. Then I need to also introduce one model is called error correction model, which is related to co-integration regression. And the last one is I will go back to the gradual causality test. Okay, if I finish all of them, I think there's no problem for all of you to do class activity number 6. Okay, all right. So let me start my class today. I share my screen. Okay, let's start with this co-integration. Okay, some of the definition, and I think we talk about a little bit about co-integration, and let me finish this co-integration topic first. Okay, and remember that we have done this Dickey-Fuller test for our example LMPDI and LMPCE. And according to our result, LMPDI and LMPCE are non-stationary. Okay, after we find out that what we call the Y or X variables are non-stationary, so if we directly doing the regression about from those non-stationary variables, then it turned out to be maybe the regression is spurious. Then the traditional approach to deal with non-stationarity is to take the first differences, then use it in the place of YT and XT, means use the first difference to replace the original YT and XT. And what do we mean by first differences? The first differences means the difference from the time period P minus the T minus 1. So usually we're using the notation as the difference. Okay, this is the notation of the difference. Okay, and but however, if we use the first difference, the first difference throws away information. Means this is really what we wanted for the YT and XT, since it is all take the differences. Okay, so it is now original the level variables. Okay, so most of the authors, also most of the researchers or econometricians, they all remind us that the use of first differences should be considered carefully, and not until the residual have been tested for co-integration. Okay, so in other words, they recommend not hurry using the first difference until we do another test for co-integration. All right, so what do we mean by co-integration? Co-integrate. So we say that co-integration consists of matching the degrees of non-stationarity of the variables in a way that makes the arrow term stationary. And by these procedures, we'll get rid of the equation of spurious regression result. Okay, and then we say that even though individual variables can be non-stationary, it's possible for linear combination of them to be stationary or say co-integrated. Okay, so in other words, let's see, for the equation 12.24 in our textbook. Okay, so the arrow terms ut becomes yt minus alpha 0 minus beta 0 xt. Okay, and actually this is ut is the arrow terms, but in fact, if we do have the data, then using the regret, this alpha 0 hat, beta 0 hat, or the estimate of the regression for yt on xt. So this is the residual. Excuse, I'm sorry. Could you?
Alin, your voice, Alin. Alin, mute your mic.
Okay, thank you. So this is actually the residual from the regressions from equation 12.24. Okay, then after we get the residuals, then we use the Dickey-Fuller test on the residuals. If we can reject the null hypothesis, then it means that the residuals are stationary. Then we say X and Y are co-integrated. Okay? All right, is that clear for all of you? Okay, so if it is, if you're clear with that, then let's go back to our example, LMPCI and PDI and LMPCE. Okay, let me go back. All right, this is our data, LMPCE and LMPDI. I think we have done the regression first to take the I think we have done the unit root test for LMPCE and LMPDI last week. Okay, so I'm going to introduce the co-integration regression. Okay, so let me consider the regression of using LMPCE as the dependent variables and LMPDI and also time, because we, according to the graph, we see, okay, let me show the graph first. Okay, I show the graph first again, okay? According to this graph, we know that both variables trend up, okay? So we know that if we can detrend, I mean, using time as one of the x variables, we can get rid of the trend variables. In other words, if I do the regression based on LMPCE and using LMPDI and an x, another time is another x, okay? Then this is the regression, and let's get the residual from this regression, okay? Originally, we already know that LMPCE and LMPDI are non-stationary. Now, after we do this regression and we get the residuals, okay? So the residual is the UI. Okay, this is the residual from this regression. And let's do the test, Dickey-Fuller test, based on the residuals. See if they're stationary. All right? Okay, so let's do it. Unit root test. Okay, since we already get rid of the trend from the original one. Okay, and by the way, after we do this regressions, and we do find the Durbin-Watson test is still very low. Therefore, unless we can test the residuals are stationary, then we may suspect the regression we just done is spurious. All right? Okay, so since we already detrained, then when we do the unit root test, we may try to find using none or intercept only. That means the version of the first version or the second version. Okay, let's try the first version. Okay, and since this indicate the first degree serial correlation, maybe. Okay, then let's try. We can try from the zero. Zero means no serial correlation, right? Okay, then we can try more legs to see the augmented Dickey-Fuller test. Okay, all right. So after I try start from the zero, so what did you see? We see the probability is very low, right? This means U1, the residuals is stationary. Okay, let's try more. Maybe the leg of 1. Okay, the probability 0.0149. Okay, still very small. Okay, this is past 5% level. Okay, and we know that our data is quarterly data, so let's try maybe up to the 4th leg. Okay, right? Okay, look at this probability, 0.0089, which pass 1% level. Okay, maybe I'll try the intercept only. Okay, I also can try from 0. Well, this probability is also small. This pass 5% level. All right, and how about 4? Well, this is past 10% level. Okay, since I tried some of them, maybe, you know, it seems that U1 can be think of as pass the stationarity test. So it passed the unit root test, means it is stationary. So in other words, let's see.
Excuse me.
Okay. Yes. Yes.
Look at the p-value now. It is 0.9. I think it is bigger than 0.45, isn't it?
But it passed 10% level. We don't have to restrict our alpha percent level to be 1% or 5% or 10%. After all, then if it is, unless you really want it to make it as a 5% level. But based on what we did for the several unit root test, most of them pass at least 5% level.
Okay, thank you.
So I will tend it, I will tend it to infer that this residual is more like stationary series. Okay. So we know that although LMPCE or LMPDI are definitely non-stationary, but the residual U1 is stationary, can be thought of stationary. Okay, so in other words, this linear combination, so to speak, cancels out the stochastic trends in these two series. Okay, so we can say that variable LMPCE and LMPDI are co-integrated. So remember the diagram we just see. Where is my diagram here? Diagram, graph. Okay. Okay. Somebody say that if you look at, since this is a y and x variables, so somebody says even two series are stochastically trained, and actually look at the difference. Okay, means they are not drift apart substantially, and they're really, trending up with the same speed. So they keep pace with each other. And actually, when we say in economics, okay, if two variables are integrated, then we say that they have long run or equilibrium relationship between them. And in our example, since our y variable is PCE, LMPCE, and x variable is the PDI, means personal disposal income, and the y variable is personal consumption, then in economic theory tell us that there's a strong relationship between consumption expenditures and the personal disposal income. Okay, and with the result of co-integrated, then the point we do this discussion says that not all the time series regression are spurious. But of course, we need to do the test like this formally. And there's one of the famous econometrician, Granger, who is the Granger, we talk about Granger causality test, okay? And he said that a test for co-integration can be thought of as the pre-test to avoid spurious regression situations. All right? And let's review. What's the difference between unit-root test and co-integration test? Anybody want to say? What's the difference between the unit-root test and the co-integration test?
Is that because the co-integration test is you can test the two variables?
Yeah, we can say so. So the difference between the unit root test and the co-integration test will be tests for unit root are performed only on the single time series. For example, individual LMPCE or LMPDI. We can do the unit root test for individual time series. However, co-integration deals with the relationship among a group of variables. So here is LMPCE and the LMPDI together. So what we do is using the regression, after we do the regression, and we test on the residuals for the unit root test. So this residual is based on the combination of LMPCE and LMPDI. Okay, the residual is coming from the combination of LMPCE and LMPDI. So co-integration tests deal with the relationship among a group of variables. And each of the variables should have non-stationary. So each of them is already, have the unit root. Then we can do the co-integration test. Is that clear?
Yes, it is clear.
Okay, then let me come back to the our co-integration regression. Okay, in other words, for these examples, this is called, since the residuals already passed the Dickey-Fuller test, therefore the original regression is called co-integration regression. And based on the co-integrating regression, we know the LMPC, LMPDI has long run relationship, which means equilibrium relationship. And the coefficient, this coefficient 0.77 is what we call long run equilibrium relationship. It means that if PDI increased by 1%, then PCE will increase by 0.77% in the long run. Okay, so this is the long run coefficient between the relationship of PCE, LMPCE, and LMPDI. Okay, now I want to come back. Oh, okay, I want to introduce, based on this co-integration theory, okay, and I think I already give all of you my PDF about error correction model. You all get it from the line, and also I put it on the e-learning system, our class e-learning system. Okay, so you may download this one, and this is not in our textbook, but this concept is important after we do the co-integration models. Okay, so I think the book in our the textbook in our class, they already refer using some words. Okay, and I like to finish this error correction model and make it, another material which I think is is also important for all of you to learn it. Okay, then after you learn this one, our class activity number 6 also have some questions from the idea of error correction model. All right, so let's see. In the language of co-integration theory, the regression A1, I think this is one I just want to refer to, is known as co-integrating regression. Also, by the way, this is what I have done for our examples. Sometimes without t, okay? Sometimes without t, if you're just using y and x, okay? And based on the residual of y and x without t. And after you do the unit root test of the residual, if it is stationary, we also can say that original regression is co-integrating regression. Okay, the t variable here is the time. Okay, this is not really necessary. Okay, whatever you do the regressions, and based on the residuals up from that regression, then test the residuals, and after they pass the Dickey-Fuller test, then this original regression is called integrating regression. Okay, so if I is using my example, since I already have the time as a variables, okay, so I'm using this example. Okay, so A1 is known as co-integrating regression, and the slope parameters beta 1 and beta 2 are known as co-integrating parameters. Okay, so we know that beta 1 is what we call long run equilibrium relationship between x and y. All right, beta 1 gives the long run impact of x on y. And also two variables, x and y, are co-integrated if they have a long run or equilibrium relationship between them. And we can treat the error terms in the equation A2. This is really the residual from A1. Okay, and A2, this one is called equilibrating error terms. What does that mean? That corrects the deviation of y from its equilibrium value given by the co-integrating regression A2. Okay, so I'm using examples later on to explain this one. Okay, so we say that if two variables x and y are co-integrated, and the relationship between the two can be expressed as an error correction model. So what do we mean by error correction model? Is like this one. So what is this? Delta yt is this delta is the first difference operator. Okay, so delta yt is yt minus 1. And ut minus 1, this one, the second term. So we know that error correction model is the original x variables, y variable, the first difference of original y variables, and the first difference of original x variables, and the lag terms of the original error terms. Okay, so ut minus 1 is the lag value of error correction terms from A2. It's this one. Okay, and vt is the white noise error terms for the error correction model. So this vt is follow the classical assumptions, means white noise. Okay, understand what I'm saying here? So error correction model is using original first difference of the y and the original first the difference of x, and using the first leg of the original regressions residuals. Okay, all right. And actually, alpha 1, the coefficient of our alpha 1 is what we call the short run impact of delta x on delta y. Okay, and since all variables A3, okay, all variables is this one, and this one. We know this is stationary. We know this is stationary, and we know this is stationary. So all the variables in equation A3 are stationary, which can be estimated by OLS. Means we can estimate A3 by OLS. All right. So for our examples, for this one, I should put the LN here. I missed the N here. Okay. LMPCE, and this one LMPDI. Okay, this is our original regression. Remember, this is long run relationship, equilibrium relationship. And UT is the arrow terms from A1. Okay, and A3 is error correction model. And alpha 1 is the short-term impact of delta LMPDI to LMPCE. Okay, so the third equation, A3 prime model, A3 prime is called error correction model. And it says that the change in LMPCI depends on changes in the LMPDI and also the lag equilibrium error terms, UT minus 1. So if this error term is 0, means if this is 0, means what? There will not be any disequilibrium between two variables. And in that case, the long run relationship will be given by co-integrating relationship, A1. So if this one is 0, the long run relationship is beta 1. Okay? But if the equilibrium error terms is non-zero, if this is not 0, if this terms is not 0, okay, the relationship between PCE and PDI will be out of equilibrium. And we know that it is interesting to know equation A3, means this one, incorporates the short run and also the long runs. Okay, let me see this one. Incorporate both the short run and long run dynamics. Okay, and also notes that equation A3, all the variables, okay, I think this is a new notations which you didn't see it before. This is I parenthesis 0, means that the original variables are stationary. So this is called integrating of order 0. Okay, so this means stationary. Okay, so you may not, you may Now I have to know this I parenthesis 0, means that all variables are stationary. This means all stationary. Okay. So that's using the example which we run the regression from this one. Okay. And I have the result from our file, but I will do that here to show you how to do it. Okay. So remember, how do we do this error correction model? We need to make the first difference of the original LMPCE, and we also need to do the first difference of LMPDI and get the lag of the U1. So how do we do that? Okay, let me show you how to do it. Okay, I'll highlight LMPCE, also LMPDI, and as well as the residual, PCE, PDI, as well as the U1. Okay, and let me open it as an equation. Okay, then I need to do the first difference of the y variables. Okay, so what we do from eViews is to use the D parenthesis. Okay, and also D, this is X variables. It's already do the differences. And what do we do from the DI? The first leg. So what we do is -1 here. Okay, this is the how we run for error correction model. Error correction model. All right. So after I do it, okay, so I hit OK, and I already done it. Then I'll get this one. Sorry, I have done this one. So this is what I have. So I have the difference for the Y, and I have the difference for the X, and also the first leg of residuals. Okay, so this is the result, and this result is exactly what we just show to all of you. Let's see this one. How to get this one to put it together. Okay, here. Okay, I have the result like this one, right? And this is what I have, exactly the same as this one. All right? Okay, so in other words, from the output, we know we have the short run coefficient. And this is the short run changes. Okay, so let me explain the meaning of this two coefficient. So let's see. Okay, I have this 0.31 almost, and this is the negative 0.065. Okay, so let's explain the meaning of this coefficient. Okay, so let's see. All the coefficients are individually statistically significant at 6%. So what we mean is, look at this probability here. Okay, this is 0.0533, so which passed 10%. Okay, this is past 1% probabilities. Okay, so we all say they're significant. Okay, all the coefficients are individually statistically significant at 6% or lower level. And the coefficient of about 0.31 shows that 1% increase in log PDI. What do we mean by the difference of the LMPDI? The difference of LMPDI means this, right? This is the LM. and this is PDIT over PDIT minus 1. If we take the log, means log, this is equal to log PDIT minus log PDIT minus 1. Isn't this is the difference of the PDIT and the PDIT minus 1. Okay? In other words, 1% increase by this one will cause 0.31% increase by the difference of LMPC. Okay, and this is the short run consumption income elasticity. We know that both variables with LN, the coefficients is considered as elasticity in economic theory. And this is the short run. And what is the long run? No, we already see the result for long run is 0.77%. So there's a difference between the short run and the long run, right? So the coefficient of the error correction terms of about 0.065 suggests that only about 6.5% of the discrepancy between long-term and short-term PCE is corrected within a quarter, since our data is quartering data. Okay, so how do we explain 0.065? Means the discrepancy between the short run and the long run within a quarter is 6.5%. And we know that it is also significant without at 10% level. Okay, not very, very significant, not very small, like 1% or 5%. Okay, and this within a quarter, suggesting a slow rate of adjustment to equilibrium. So, the rest of the reason are maybe is our prediction. Okay, one reason the rate of adjustment seems low is that our model is rather simple. So if we have other data of interest rate or wealth consumers and so on and so forth, probably we might have seen a different result. Okay, so this is the definition and examples for error correction models. I think it is important for all of you to know, not just only for the co-integration regression only, because they are so close together. They are related. And also, I'm going to use this same example to go back to talk about granular causality. Or remember that granular causality, we talk about it in 12.3, maybe. Let me see from our textbooks. 12.4, granular causality.
Prof,
Since we need to, yes.
Actually, like yesterday, I'm searching on in the internet, like how to do the error correction model, and the way they're showing is like they remove the constant. So I am like questioning like what is the difference between removing the constant and having the constant?
You mean, what do you mean by moving the constant?
So when we running the model, they're removing the constant. like the
Uh,
C factor.
You mean this one?
Yeah.
You mean the one I just showed it for the A1? They are removing beta 0? What do you
Yeah.
mean
Then
by, so there's, when they use the error correction model, then this is our original co-integration regressions, right?
yes.
For, you know, for A1 prime, A1 prime, this is our original co-integration model. And this is our error correction model. So which are you talking about? Is this one? They don't have this one?
Yeah, they don't have a alpha 0.
Alpha 0, you mean this one?
Yes.
You mean they don't have this constant terms for A1 through A1 prime?
Yes.
Usually we do have constant terms. Usually we do have it. I don't know what kind of textbook you're reading or what kind of articles you're
Actually, like
reading.
I'm watching online and like on YouTube, and they're saying, like I'm searching is like how to run error correction model on Gradle, and that is the
Yeah.
way they are like showing us. So I'm just
Well,
like
actually,
confusing.
just for our examples, okay? This one is our co-integration regression, right? And this is error correction model. Actually, we all have the constant terms. I didn't see, as far as I know,
Yes.
we do have constant terms.
Okay, I got it.
All right. Any other questions?
Prof, I see the value 0.77%, 77%. This is from where, Prof?
You mean the result?
The result, yeah. We have to run individual first and then to go the
You mean this
Maslow.
one?
Yeah, the result, you explain the notice. Don't know, Prof.
Which one?
Next
one,
next page. The
Huh?
the explanation. The result.
Explanation. Okay.
Yeah.
You
Yeah.
mean explanation? Here.
Explanation. This one, Prof. 0.70%.
You mean where did the 0.77 coming from?
Yes, Prof. We
Okay,
have
this
to
is
running, yeah,
this
by
the
individual.
0.7. This is the called long run equilibrium. And this 0.77 is from here, running the regression of this. So if I show our own result, this one, 0.77 is here.
It
And
means we're running.
is this
Yes.
Is this your question?
Yeah, this is the equation. It means, oh yeah, because not enter
This
in
is
the you. Yeah, I understand, Prof.
This
It
is
means we have to running individual first and then to got the LPDI.
yeah, sure. So
Yeah, yeah.
so without running this one, you don't have the residual terms,
Yeah, Prof.
and
Okay, Prof.
you have to test the residual term to make it stationary. Then you can have the co-integrating regression. Then after that, you will have error correction model.
Yes, Prof.
That they're all related.
Okay, Prof. Thank you.
Okay. Well, why don't we stop here for the first meeting, I will come back at the second meeting. Okay, I will continue this topic. Okay, all right. I'll stop recording.